time to introduce another function, and this is called the gradient function. So we know that the function, y equals function x, measures how far the graph is above or below the x-axis. In other words, the y-coordinate. Well, the gradient function measures how steep the graph is at that particular point. Another way of thinking about that is it's the rate that the distance above or below the x-axis is changing. Another name for the gradient function, which you might have heard, is the derivative. Now, geometry is a great way of finding the gradient of function lines, but it's very limited. We can use it for lines and semicircles. So let's first of all look at lines. So horizontal lines, well, that's pretty straightforward because we know that the function is a constant value, and we know the slope of a constant value is always 0. So its gradient function, it doesn't matter what the x value will be, is going to be 0. For an oblique line, so y equals mx plus b, we know the slope is the coefficient of x. So the derivative would be m, the coefficient of x. So that's pretty straightforward. What about a semicircle then? So here's our standard semicircle, square root of r squared minus x squared. Now, unlike a line, we don't have a consistent slope. As we move around the semicircle, the slope would change. And when we're talking about a curve, the slope of a curve is the slope of the tangent we would draw at that particular point. So, all right, at this point A would have an x value and it would have a function x value. The other thing we know about semicircles is that the radius is always perpendicular to the tangent. Now we can work out the slope of the radius at any point. It would be the function value over the x value. And we know that lines perpendicular to each other multiply together to give -1. So the slope of the tangent would be the negative inverse, minus x over function x. Well, function x, remember, is the square root of r squared minus x squared. So our formula for the gradient function would be minus x over the square root of r squared minus x squared. Now, any other graph, we're going to have to estimate using secants. So let's have a look at a quadratic. Here's our standard parabola, y equals x squared. If I want to find the slope at this point here, 2, 4, so what's the gradient function? Well, choose a couple of points either side of the point you're interested in. So either side of 2, 4. So I'm going to use 1, 1 and 3, 9. I'm going to calculate the slope of that secant and I get a slope of 4. So my estimate for the slope at 2 would be 4. Now, it's a reasonable estimate. Obviously, where you choose A and B becomes very important. The advantage of a quadratic is that if I choose an even amount either side, it works out quite nicely. And in fact, it is the correct answer. Okay, so here's our parabola. If I pick any point, x squared, I'll pick a point either side. I'm going to make it symmetric. So x plus h and x minus h. Using our slope formula and playing around with the algebra, we get the answer as 2x. So I'm claiming that the gradient function for our standard parabola, x squared, is 2x. And indeed, that is the correct answer. Now, as I've said, because if I choose them symmetrically on a quadratic, then I'll always get the exact answer. Hyperbola, okay, I'll pick the point 2.5. I'll try the same idea. I'll pick symmetrically. So I've got the point 1, 1 and 3 1/3. So slope is negative 1/3. So my approximation is negative 1/3. Well, that actually is not the correct value. Unfortunately, a hyperbola doesn't work as well as the quadratic. Turns out it's actually minus 1/4. The other thing that's vital when we're choosing our points is the graph needs to be continuous. Say I chose C down there and I use BC. Well, you can clearly see from the picture that estimate's not great. So if you have an accurate graph, and that's an important point there, an accurate graph, then it's usually going to be better just to simply draw the tangent in and then use rise over run. Okay, we'll have a look at exercise 9A.